And welcome. In this example, we're going to look at how to determine the RMS voltage across R3 resistor. So our R3 is down here, and we're looking for VRMS. And so that's going to be our goal, and we're going to work towards that. So we need to figure out two things about R3. We don't know its resistor value, we don't know its ohmic value, and we don't know the current through it. We do see that this is a series circuit. There's only one pathway for current to flow through there. That means that whatever IT is, that's going to be the current through this resistor also. And so if we can find IRMS, then we'll be able to use that to find VRMS. Okay? And we can't use resistance for that because we don't know the resistance of this component, but we can use KCL or even KVL. If we found the voltage drops of all the other ones in RMS, we could use KVL to determine that also. There's many pathways that we can go. So let's figure that out, and we'll work with getting everything into the same notation because we were given peak volts here. We're given peak to peak, the peak to peak up here across this R1 resistor and its value. So we know two things about that. So we can use that to determine I peak to peak, right? Or if we swap out our peak to peak voltage that we know across that then into VP, then we'll be able to determine IP, right? We just got to match them up. We also see that this multimeter right here is measuring around R2 and getting a voltage out, and we know that that multimeter should read VRMS. So we know the VRMS voltage drop across R2. We know nothing about R3, and we know just the resistance of R4. So we can go after our voltages, right? We can go through and find the voltages of everything we do know about because we have a voltage for R2. We have a voltage for R3. We know nothing about R4, but we know that we can find the current IT, since that's the only current in the circuit, through this one resistor here, and that's going to be the current through all of them. So at that point, we would know IT current through R4 as well. And then we got two things, right? Ohm's law says if we have two things, we can use those two things to determine that last third thing, which would be our voltage drop, the voltage drop across R4. In whatever state that we got it in. So if our IT is in peak to peak, then we would have the peak to peak of this. We just got to watch out for that because we can only subtract peak to peak voltages from other peak to peak voltages. So since our final goal is actually RMS voltage, we might switch all of these into RMS voltage, figure out the voltage drop in RMS for each one of these resistors, and then use KVL. KVL says if we know what our voltage source started out as, we can subtract what the voltage across R1, voltage across R2, and voltage across R4 have, and we'll end up with the voltage drop left over R3. And since we want that in RMS, we might as well put all these other ones in RMS so that we can make that subtraction easier on us. So that's going to be our pathway. So our first goal is to convert our source voltage into RMS. We know it's in peak, and so we can say that our voltage source in RMS is actually equal to our VP multiplied by 0.707. So we can solve for that out here. That we have 28.3 multiplied by 0.707. That gives us 20. We use that. We'll say that our VRMS is equal to 20 volts. We'll round that off even. And that's an RMS now. Right, so that's our peak. That's our total voltage, VT. So we'll write that at the top here. VT RMS is equal to 20 VRMS. Okay, now we can move on to our next one. We know that we have a peak to peak up here. And so we can take that peak to peak and divide it by 2 to get to our peak voltage. We can say that our VP is equal to the peak to peak divided by 2. And once we get that, we'll end up with our VP, and then we could multiply that by 0.707 to get to our VRMS. So that's what we're going to do. We'll say that we have a peak to peak of 12.3. We'll divide that by 2. That's our peak voltage. And then after that, we'll multiply that by 0.707. That gives us 4.34 voltage drop. 4.34, round that up, 3.5. The RMS. So now we know our voltage drop across this one, not in peak to peak, but actually in our RMS form. So we know what that voltage consumed, 4.35 VRMS. Right? So immediately we can look at this and say, well, this one was also VRMS across R2. R2 must be larger than R1, right? Because R1 has less voltage drop, therefore it's a smaller resistor in our series circuit. So we can move on here. Now that we know our RMS voltage and the resistor value of R1, we can use that to find that current that we talked about, right? IT. We'll go after that next. We'll say that our IT says Ohm's law, and Ohm's law allows us to put IT equals our voltage drop. So VR1 divided by the R1 resistor. They have to match, right? Have to match. We'll set this out and we'll calculate it. We'll say that we have a voltage drop RMS value of 4.35 divided by a total resistance for R1 of 13,000 or 1,300, and then we'll plug that in. That's our total current for the entire circuit. So we'll say that that is 0.0033, and we can move that decimal point back, 35, and we'll get that at our milliamp value. So our total current is 3.35 milliamp. And that's in RMS. So we can use that. We can use that against our R4. We know R4 has that same current. That's going to get that 3.35 MA RMS. Now that we know two signs about that, we can use Ohm's law again. We can say that our Ohm's law gets voltage, current, and resistance. And if we know our resistance and our current on the bottom, we can solve for voltage. We can say that the VR4 voltage drop in RMS is equal to our current in RMS multiplied by our R4 resistor. And specifically, it's going to be our total RMS. And we can set that equal there and solve it out. Say that we have 3.35 milliamps, so 0.00335 multiplied by our 680, get 2.278. So the voltage drop across R4 up here is 2.278 volts. 278 volts, RMS. So now we know the voltage drops across all of them. Our meter originally gave us RMS voltage. Our RMS voltage for R1 is given. We found the RMS voltage for our original source voltage, that was 20. And now we know the voltage drop across R4. So all that's left is the voltage drop across R3, which we want to know in VRMS anyway. So now we can use KVL, apply KVL. This out, and we'll say KVL says our source voltage gets to subtract out all of our drops, and that's going to be whatever we're left with. So we started out with a VRMS total voltage of 20. We lost 4.35 across R1. We lost 8.366 across R2, and we lost 2.278 across R4, which leaves us with 5. The RMS across R3. Let us know if you guys have any other questions.